Hi everyone. Today we are going to start a new topic, that is the laws of motion. As this is the first lecture, we are only going to cover the basic understanding that will include the background of these laws of motion. The background meaning that how these laws of motion they were formulated, what all scientists they contributed to these laws, and how they were finally written down. So, from our previous lectures, from our previous chapters, we know that the uniform motion means the constant speed, that is, no acceleration. And non uniform motion implies that the body is moving with some acceleration, and so the speed of the body is either increasing, and if the body is moving with some retardation, the speed of the body will decrease gradually. Introduction today. So the first question regarding this uh, concept, it was that what governs the motion of bodies. For example, if we say that a glass of water which is kept on a table, it has to be picked up. I mean, it cannot move on its own. We will have to pick up from our hands by using our hands and then drink it. Another example, if we see that a football is at rest, then it has to be kicked to move it. It cannot move on its own. And also, for a person, if we say on a person on the cycle has to pedal to move the cycle from one position to the another position. The cycle cannot move on its own. It's not just that the person will sit on the cycle and it will move on its own. It does not happen. When we observe these kind of things around us, we can conclude that the external agency is needed to provide a force to move a body from rest. Similarly, we can also say that some kind of external force is needed to retard or stop the motion of the body. For example, when you see a ball is coming towards you and you catch that ball using your hand, then it comes to rest. If you will not catch it, if you will not use your hands to stop it, then it might go to your face and hit your face. So, in simple words, if we understand this thing, that some external agency is needed to provide a force to move a body from rest. अगर कोई बॉडी रेस्ट स्टेट ऑफ रेस्ट में है, मूव नहीं कर रही है, अपनी जगह पर है, देन वो अपने आप नहीं मूव कर सकती है. कोई ना कोई एक्सटर्नल फोर्स हमें प्रोवाइड करना पड़ेगा ताकि वो अपनी जगह से दूसरी जगह पे मूव करे. और सिमिलरली अगर हम कोई चलती हुई बॉडी के बारे में बात करें, तो वो अपने चलती हुई बॉडी अपने आप रुक नहीं सकती अनलेस एंड अनटिल हम कोई एक्सटर्नल फोर्स दें ताकि वो रुक जाए. So in the examples that we discussed above, the external agency of force is in contact with the object. जैसे if we talked about the glass of water, it has to be picked up by our hands. So हमारे hands जो हैं वो contact में है glass of water के. The football, when we are kicking the football जो है वो हमारे feet के साथ में contact में है. And the person on the cycle, when he is pedaling the cycle, the feet of the person they are in contact with the pedal of the cycle. So the external agency of force is in contact with the object. But we'll also observe that this is not always necessary. For example, if we say that if we throw a stone down from the roof of a building, we have discussed in the previous chapters also that it will fall down freely due to acceleration due to gravity, which is acting vertically downwards. That's minus g. We were talking about in the vertical motion. So in that case, if we observe the motion of the object, when the object is falling down, when that stone is falling down, it is not in contact with any body. We have simply just thrown that stone. So it simply means that being that the external agencies they can even exert a force on a body from a distance. Like in the motion of that stone is governed by acceleration due to gravity, and that's not in contact with that stone. So कोई एक्सटर्नल एजेंसी अगर फोर्स लगा रही है बॉडी पे, तो ज़रूरी नहीं है कि वो एक्सटर्नल एजेंसी उस बॉडी के साथ में कॉन्टैक्ट में हो सकता है अगर वो दूर से भी वो फोर्स एक्सर्ट कर पा रही है, देन ऑल्सो द बॉडी कैन गेट इनटू मोशन. So, this was the basic introduction about the laws of motion, like what all, like what governs the motion of bodies. So, now we are going into the background of these laws of motion, and we will talk about certain scientists who contributed to this topic through their work. Some of the scientists they were wrong, and some of them they were correct. So we will talk about them. So the first person to contribute to this concept, to this topic, was Aristotle. So what we have discussed now was, like, we were talking about the starting question, and here what we discussed was regarding to this question. And similarly, and now we are going to talk about Aristotle's laws of motion. So he was the first person to contribute to this concept of laws of motion. So, so we have seen that some external force will be needed to to move a body from rest, and if we want to stop a moving body, then also a force would be needed. Now, if we are talking about a moving body, so the question arises: is an external force required to keep a body in uniform motion? मतलब अभी हमने अभी हमने ये देखा कि हाँ, अगर कोई बॉडी रेस्ट पे है तो उसे मूव करने के लिए हमें फोर्स लगाना पड़ेगा, अदरवाइज वो मूव नहीं करेगी अपने आप. दूसरी चीज, अगर कोई बॉडी मोशन में है एंड इफ वी वांट टू स्टॉप दैट बॉडी, तो भी हमें एक्सटर्नल फोर्स लगाना पड़ेगा, अपने आप वो नहीं रुकेगी. अब जो थर्ड क्वेश्चन हमारे पास ये आता है कि इज एन एक्सटर्नल फोर्स रिक्वायर्ड टू कीप अ बॉडी इन यूनिफॉर्म मोशन. मतलब कि अगर कोई बॉडी यूनिफॉर्म मोशन में है, दैट इज वी हैव ऑलरेडी सीन दैट मीन्स the body is moving with a constant velocity. So if a body is moving with constant velocity, तो क्या एक्सटर्नल फोर्स हमें लगाना पड़ेगा जिससे कि वो यूनिफॉर्म मोशन में बनी रहे, और या तो वो अपने आप यूनिफॉर्म मोशन में बनी रहेगी विदाउट एनी एक्सटर्नल फोर्स. सो दिस वाज द क्वेश्चन दैट वाज आंसर्ड बाय एरिस्टोटल फर्स्टली. लाइक उसके बाद बहुत सारे साइंटिस्ट ने इस पे काम किया था, एंड वी विल आल्सो डिस्कस द later things. So the law of motion, which was first given by Aristotle, is simply said that an external force is required to keep a body in motion. So उन्होंने सीधी स्टेटमेंट से he simply said, let me write this down. He answered this question by his law, which said an external force is required. So this was the statement which was given by Aristotle. For many of you, this statement might seem pretty normal through our common experience that one needs to apply some force for keeping a body in motion. Like, for example, if we take a very common example, that's a small child is playing with a toy car, and that toy car is attached to a string. You must have seen those toys, they are attached to a string, and the child, it drags or pulls that string forward to keep that car moving. So in that case, we might also say that yeah, this statement is correct, because उस बच्चे को भी पता है कि when he'll stop pulling that string, that car will come to rest. That's why he keeps on pulling the string forward to keep that car in motion. So, but this is not the complete picture. There is something else that we need to consider here. This law of motion, which was given by Aristotle, it seems correct in the practical scenario because this is what we are observing. But that's because there are many other forces in the acting in the background of a body that we need to see something else. This statement is completely wrong in the ideal conditions, but practical scenarios it is correct. So if we are talking about that same moving toy car example, we can say that that the frictional force, everybody must be aware of, or at least they must have heard about the frictional forces. Like frictional forces, they basically come into role only when a body is in motion. Like if something is kept on a table, like if some book is kept on a table, then it will not experience any frictional force. But if we try to drag that book on that table or move that book on that table to the left, then when that book comes in motion, then only the frictional forces they start acting on that book. So talking about the frictional forces was let me clear this thing. Like see if this is a book, this is a table, horizontal table, and some book is kept on that table. When it is at rest, no frictional force will act because these are the kind of forces which are opposing in nature, opposing to the motion of that object. So suppose we move this book towards right, and so frictional forces are opposing in nature. They are very natural forces, and so these forces they will act in the left direction. See, so this will be the friction. This will be the direction of the frictional force. They will act along the surface which is in contact, which is in between the book and the table. So this is the direction of the frictional forces. Let it be F. So these forces, just remember that these forces they act only when the object is in motion. Otherwise, they will not act. So coming back to our moving toy car example, when suppose that the child stops dragging or pulling the string of the toy car, so we'll observe that the toy car will come to rest. But this is not because he has removed his force from the string. It is because the external forces of the friction on the car by the floor they oppose its motion. That is when the car in this example also when a car, suppose this is the car and this is the string which is attached to that car, and the child is pulling down the string. The child is moving forward and the car will also move forward. As soon as the child will stop dragging the string, the toy car will come to rest. It is only because the frictional forces they are acting in the opposite direction. They will be acting here in this direction. They will be acting in this direction. Will try to stop the car. So we can say that actually what the child is doing is to move the car. He is providing the same amount of forces, the same amount, that is if every other frictional forces, then he will apply the same amount of force or even more than that. So the child, suppose he applies force F, this F should always be greater than this frictional force small f. Only then the car will be able to move forward. So when the child pulls the car with the same force forward, the net force becomes 0. And so the car will move in the uniform motion, that is with the constant velocity. So as I talked that even if we are seeing a body at rest or in a uniform motion, we just cannot simply say that no forces are acting on the body, because there are many background things that are happening during the motion of the body. So these frictional forces, they always act. They are very natural, and they also are the reason for the deviation from the ideal condition. So the conclusion that now we draw from this concept is that this was a scenario when the friction is present. That is in the common practical scenario we are talking about. And if there were no friction, suppose if there were no friction, which is not possible actually, but let's suppose that if there were no friction, the external force would not be required to keep the car in motion. I mean, in simple words, if we say that when a child, जब child string को pull कर रहा है, तो actually he is not providing the force for the to keep the body in motion, बल्कि वो क्या कर रहा है कि जो already frictional forces लग रहे हैं body पे, वो जो फ़ोर्स प्रोवाइड कर रहा है वो उन फ्रिक्शनल फ़ोर्सेस को बैलेंस करने के लिए प्रोवाइड कर रहा है, ताकि कार जो है वो रुके ना और यूनिफ़ॉर्म स्पीड या कांस्टेंट वेलोसिटी से आगे चलती रहे। सो इफ अगर फ्रिक्शन नहीं होता, इफ देयर वाज़ सम आइडियल कंडीशन एंड इफ देयर वर नो फ्रिक्शन, देन उस चाइल्ड को एक्सटर्नल फ़ोर्स लगाना ही नहीं पड़ता टू कीप दैट कार इन मोशन। अपने आप चलती रहती वो यूनिफ़ॉर्म मोशन में। So, but these opposing forces, they are always present in nature. Like frictional forces are there in the case of solids, and similarly, the viscous forces, we call them viscous forces, are there in the case of liquids. So, this is the reason why Aristotle's laws of motion is not considered right. मतलब they were, as you must have read somewhere, that these are known as Aristotle's fallacy. Fallacy means something that is not right. That was considered right, but that is not actually right. So that was the conclusion of all this. Let me again keep this thing in simple words because it might seem a little bit confusing for some people, but it's very simple. So for the first case, if it summarize everything, if a body is in a state of rest, अगर कोई बॉडी स्टेट ऑफ रेस्ट में है, बिल्कुल मूव नहीं कर रही है, देन हमें एक्सटर्नल फोर्स लगाना पड़ेगा उसे मूव करने के लिए। अगर कोई बॉडी मूव कर रही है, स्टेट ऑफ मोशन में है, तो हमें एक्सटर्नल फोर्स लगाना पड़ेगा उसे रिटार्ड करने के लिए या फिर उसे रोकने के लिए, अदरवाइज अपने आप वो नहीं रुकेगी। और जो तीसरा केस है दैट इज ये अभी जो हमने एरिस्टोटल्स लॉज ऑफ मोशन में डिस्कस किया, वो क्या है कि इफ अ बॉडी इज इन अ यूनिफॉर्म मोशन, यहाँ पे ये ध्यान देना है कि हम लोग सिर्फ यूनिफॉर्म मोशन के बारे में बात कर रहे हैं, दैट इज इट इज मूविंग विद अ कांस्टेंट वेलोसिटी, इट इज नॉट एक्सेलरेटिंग। अगर एक्सेलरेशन आएगा दैट अब हम लोग आगे डिस्कस करेंगे एक्सेलरेशन वाला केस भी। तो थर्ड केस बनता है कि व्हेन अ बॉडी इज मूविंग इन अ यूनिफॉर्म मोशन, एरिस्टोटल ने बताया था कि सम एक्सटर्नल फोर्स विल बी रिक्वायर्ड टू कीप अ बॉडी इन मोशन, बट that was a wrong statement. That was, or if we may not consider it as wrong, we may say that this was a statement that only considered the practical applications. So what Aristotle did was he just simply what he saw or what he observed in practically around him, he just told it as a law, but that's not right. So this statement is only valid for the practical cases. So for in ideal cases, if we say, then when there is no friction, so external force will not be required to keep the car in motion. So we can write here, this is only true for the ये practical observation and that's it. This is not the complete picture. अगर हम लोग ideal situation के बारे में बात करें, ideal situation simply means here in this case it simply means that no friction forces are there or no viscous forces in case of liquids, no viscous forces are present. So thus the Aristotle's laws of motion, they are not considered right. Now we are going to talk about the law of inertia. So we'll also see that what actually in the word inertia means. So after Aristotle's laws of motion, after many years, Galileo studied the motion of objects on an inclined plane. So what he observed was, so now we are going to study about Galileo, like how Galileo contributed to all this thing. So now we'll talk about Galileo. So basically what he observed was that the objects which are moving down an inclined plane, they always accelerate, and the objects which are moving up the inclined plane, they always retard. So let me draw this condition is what he observed was in his first experiment. He did two experiments related to this. So we are first studying the first one. So he observed that suppose this is the floor and this is an inclined plane, an object which is going down an inclined plane. Suppose there's a ball and it is moving down an inclined plane. So he observed that it will always accelerate. That is, this is not a uniform motion. Here the velocity will increase. It simply means that if it is accelerating, and another case, he observed that if this is an inclined plane And if a ball is made to move up, obviously it will not go up on its own. We'll have to move it up. Like we have some given some initial force to the ball, and so it will move up an inclined plane. And so it was observed that it always retards, that is, its velocity reduces. So he said that since the motion on a horizontal plane is intermediate between these two cases, because inclined plane is just tilted, and so the motion on a horizontal plane, it can be considered as a intermediate between these two cases. So the object, when it is moving on a frictionless horizontal plane, it should move with constant speed. So the intermediate condition, or we can draw it in between these two diagrams. The intermediate condition is when a body is simply moving on a frictionless horizontal plane. You should pay attention to the word frictionless here because we had just discussed about friction. So the friction plays a very, very important role in the emotions. So you should pay always attention to this kinds of words. So if this is this is an intermediate case between these two. So when a body is moving on a frictionless horizontal plane, it will keep on moving with the constant velocity. Like it will always keep on moving in the uniform motion. So this was his statement, because see, this experiment he can do, this also experiment he can do, but he cannot do this experiment. So he just conferred or concluded from these two experiments that this third case will happen, because see, he told it to be frictionless. You can try oiling the surface, for like using oiling the surface, so you can that oiling will help to reduce the friction between the ball and the plane, between the ball and the horizontal surface. But eliminating friction completely, like if keeping the friction zero, cannot be a case. It is not even possible. So that's why uh, he concluded this. Now, he also did another experiment that is known as the double inclined plane one. So the second experiment that he did was the known as the double inclined plane. So, so what is a see? This is a double inclined plane. It's nothing. It's one inclined plane is it's going down like this, and the another inclined plane is going up like this. So, so he did an experiment that a ball, when it is released from rest, from suppose from this point, when it is released, it rolls down. It will roll down like this, and it climbs upon the other inclined plane. If these planes are considered to be smooth, I mean they do not have a lot of friction. I mean the person can try to reduce the friction. So if the planes are smooth, the final height is observed to be nearly the same. So he was talking about this height. See, the height from which the ball was released, that is h, and the final height which the ball again reaches is also h. So these two heights, they came to be the almost equal, because in the practical cases some friction would be there, so the height can be a little less than the previous height h. Now what he did was, in its another case, this is the ground, this is the floor. What he did was he reduced the slope of this second inclined plane. The first inclined plane will be of the same height, like same slope as was before, and the second inclined plane. Now let me redraw this. See, this is the decreased slope. Now it will be more clear. So this inclined plane has a more slope, and this inclined plane has a lesser slope. So when the ball is released from the same height h, suppose this is the ball and it is released from this height is h. So what was observed by Galileo was that this ball will also roll down. It will also start climbing up the other inclined plane. But here, the slope of the ball does not matter. The ball will again reach to the same height h. It will have to travel more distance, because see, this distance, the slope of the inclined plane, this surface of the inclined plane length would be less, and this length would be more. So it will have to travel a longer distance as compared to the first one. But again, he observed that the ball will reach the same height edge. So in the limiting case, like if we observe these two cases and we say that we create a limiting case that when the slope of the second plane is zero, like we keep on decreasing the slope, like we have decreased the slope to little, and then we'll continue decreasing the slope of the second inclined plane, and then we'll finally reach a situation that limiting case would be there when the slope of that inclined plane is reduced to zero. So this is the limiting case when the slope of the second inclined plane is zero. The ball should travel infinite distance. That is, it will never ever stop, because actually see the, we can consider that here the goal of the ball is to reach the same height edge. So here we can see that if we draw this limiting case, this is the ground, and when the ball is released from some height edge, so basically the ball will want to go back to the height edge again. But because we do not have any other inclined plane, so it will keep on moving forward. It will keep on moving forward with a uniform speed. See, and it will never stop. It can go to the infinite distance also, and it should never stop. So, but again, it cannot be the case, no, because we have friction in practical scenarios. So this was also this limiting case was also concluded from both these above cases. So this was Galileo's conclusion from his second experiment, which is also the same as the first experiment. So this third case is, as we can write it here, that this is the ideal condition. This is, it can travel to infinite distance, matlab it will never stop. Now again, you can relate the same thing with what we discussed in that toy car example. That even if that child stops pulling that string which is attached to the toy car, it should keep on moving. Like I mean, the child को जरूरत ही नहीं है वो force लगाने की to keep that in motion. Even अगर वो छोड़ देगा string को, so the toy car should keep on moving. This is the same case. This is the same case which is related to this third case. This is the ideal condition. Practically, if we say that this ball will come to rest after moving a finite distance because of the frictional forces. So if we talk about the conclusion from these Galileo's experiments, so the first conclusion that we can draw from Galileo's experiment is the state of rest and the state of uniform linear motion are equivalent. And the second conclusion which was given by Galileo is the body at rest continues to remain, continues to be, and a body which is in uniform motion continues to be in uniform motion. So let me first again explain this in simple terms. So the first statement says that the state of rest and the state of uniform linear motion are equivalent, as there is no net force acting on the body. So in simpler words, अगर कोई बॉडी स्टेट ऑफ रेस्ट में है, मतलब वो बिल्कुल भी मूव नहीं कर रही है, उसकी वेलोसिटी जीरो है, एंड सम अनदर बॉडी जो कि मूव कर रही है लेकिन कांस्टेंट वेलोसिटी से मूव कर रही है, दैट मींस दैट देयर इज नो एक्सेलरेशन इन्वॉल्व्ड. ये जो दोनों स्टेट्स हैं दे कैन बी कंसीडर्ड इक्विवेलेंट. क्यों? बिकॉज देयर इज नो नेट फोर्स एक्टिंग ऑन द बॉडी. So this word net, that's very important here. This word net, let me first explain you what this net force actually means. So the net force is that when we were studying about the vectors and the resultant, we were using the triangle law for calculating the resultant vector. So here also force is also a vector quantity, you know, because it also has a direction involved with that. In which direction? If we are pulling a wall, suppose if we are pulling a wall, if we are applying some force on that wall, so that force will have a direction. So therefore the force is a vector quantity. So this net force here simply means the resultant that we took out using the parallelogram law or the triangle law. The net simply means the resultant. So the resultant force which is acting on that body should be zero. So if a body is in a state of rest, then also the resultant force is zero. And when a body is moving with a uniform, with a like with a constant velocity, then also the resultant force on that body is zero. So therefore, Galileo said that these two states, that is the state of rest and the state of uniform motion, they can be considered as equivalent. Obviously, they are different because one in one case the object is at rest, वो move नहीं कर रहा है, and in the second case object जो है वो constant velocity से move कर रहा है, लेकिन उनका जो बैक एंड या उनका जो बैकग्राउंड है वो सेम है, क्योंकि दोनों में ही नेट फोर्स जो लग रहा है वो जीरो है. एंड द सेकंड स्टेटमेंट हियर सेज, in case of zero net external force, again see here the word net is there, that we are talking about the resulting external force. The body at rest continues to remain at rest. मतलब जो बॉडी रेस्ट में है वो रेस्ट में ही रहेगी, वो अपने आप नहीं मूव कर सकती है. कब? जब नेट एक्सटर्नल फोर्स जो है वो जीरो है बॉडी पे, और जो मूविंग बॉडी है वो मूव करती रहेगी, मतलब यूनिफॉर्म मोशन में है तो वो कांस्टेंट वेलोसिटी से मूव करती रहेगी अगर उसके ऊपर नेट एक्सटर्नल फोर्स जो है जीरो है. मतलब मे बी द बॉडी के ऊपर बहुत सारे फोर्सेस लग रहे हों, फोर्स F1 F2 F3 अलग अलग डायरेक्शंस में लग रहे हों, एंड वी कैलकुलेट द रिजल्टेंट फोर्स using the triangle law of addition. So when we calculate that resultant force F, it should come out to be zero. Or in other words, we can say that all the forces, they must cancel each other out. So जो नेट फोर्स रहेगा वो जीरो रहेगा, एंड उस कंडीशन पे जो बॉडी की स्टेट है वैसी ही रहेगी. अगर वो रेस्ट पे है तो वो रेस्ट पे ही रहेगी, और अगर वो यूनिफॉर्म मोशन पे है तो वो यूनिफॉर्म मोशन पे ही रहेगी. So now you can see that these statements, they are completely opposite with the statement of Aristotle. जिन्होंने क्या बोला था? Aristotle's statement was that we do not need, like no external force is required to keep the body in uniform motion. तो Aristotle ने बोला था कि if we want to keep a body in motion, in a uniform motion, then हमें खुद से external force लगाना पड़ेगा. And Galileo's के जो conclusions निकले experiments से, they were totally opposite. So now we will talk about this property of a body called inertia. So this word inertia. So this property of body, जो property of body that we talked about in the second statement, that the जो body का state है, जो if it is in the state of rest, it will continue to remain at rest, and if it is moving, it will continue to keep on moving in with uniform speed. So ये जो property है body की, इस property को हम inertia बोलते हैं. So inertia simply, in simple words, we can say inertia means resistance to change. Resistance to change means वो change नहीं होना चाहती. Resistance, वो जो भी उसकी state है body की जो property होती है inertia, वो उस state को change नहीं करना चाहती है. It tries to maintain that state of that body. So if we simply summarize it up, so we can say that no external force is required to keep the body in uniform motion in the absence of frictional forces. So गैलीलियोस के जो ये conclusions थे ना, ये बिल्कुल ideal conditions पे थे, मतलब जिसमें हम friction को consider नहीं करते हैं. We'll also consider the we'll also do the practical problems, the numericals later on when we'll study all the laws, all the three laws of motion, where हम लोग numericals करेंगे, जिसमें कि we'll consider the normal forces, that is the gravitational forces, the frictional forces, and then we'll talk about the motion of that body practically. But the laws of motion दिए गए हैं, the three laws of motion, the famous Newton's three laws of motion, they are being they have considered the ideal scenarios. So this was all for today. We talked about Aristotle's fallacy, and then we also talked about Galileo's ideas and experiments. So in the next lecture, we'll go on to Newton's first law of motion, and we'll say that Isaac Newton, he basically used Galileo's ideas for his laws of motions, and he extended these to somewhat extent. So we'll end the lecture here only. Thank you.